So there was a vulnerability in the Linux kernel that allowed privilege escalation for around 10 years. It's called Dirty Cow. It's named CVE 2016-5195 because it was named in 2016. And it allows unprivileged users to write to read-only files. So for example, read-only file is a ping, um, and ping actually runs as root because it is able to send special packets that other programs can't. And you could write to ping and have it execute other instructions as root than it's normally designed to. So you could have it change the root password, for example. Um, and if you just want to see that for yourself, you can stat the uh, ping binary, and you can see that you are able to read it and execute it, but you are not able to write to it. And I have this file here, adminlist.txt, that we're going to write to in a little bit, that you also can't write to. This one's just read-only, not executable or anything. And if we do read it, we can see that our admins are just user01 here, but we're going to change that to hacker later. And I think you can contrive an example where you could do some nefarious activities by doing that. And I will make a CTF for this. That it's going to be hard to give all the hints for this because this involves using system calls and all of that, but it's not just uploading a file to a server. Anyway, so how are we going to do this? We're going to use, I already have it drawn out here. We're going to use a race condition in the way that the memory manager works in the kernel. And actually, to clarify, this is kernel version 3.11. I'm on Ubuntu 12.04. Any version before 4.30 is vulnerable to this. And if you're running Linux, you're probably using like version 6 right now, so you don't have to worry about this vulnerability. But the way this one works is we have our disk, which has, say, ping on it, and we can open that file and map it into our memory. And I might want to actually just get rid of some of this stuff so I can do it one at a time here. I'll put back this. Okay. So we map ping into memory, and as a user, we can read from it. At least on this section, we can actually read or write to it when it's in RAM, because once we've read the memory, we can use it for our own purposes. We can copy it, do whatever we want. But for optimization reasons, if we're just reading from it, the kernel will only have one place in RAM where that file actually exists. So an example here is if you have our user and the root both using ping, root can of course write directly into this, or it can write to this file that will then be written back into the real memory or into the disk. But our user can't write into this section. If we want to write to our personal version, our private version of this file, we would do, or the kernel would do something called a copy on write. So a copy on write basically happens when you have memory that's your own, but is being used in a way that it can be shared. But then because you write to it, you can't share that memory anymore because it needs to be different between, say, the root and you. Um, so the kernel will copy that memory over to here, do whatever write you asked it to with the write system call, and then it will translate your virtual memory addresses to, instead of pointing to this region, to point to this region. And of course, this is your own private piece of memory as a process. You can do whatever you want. You can read or write to it. And that's a very efficient way of doing things. And to improve efficiency even further, we can actually we can give the kernel hints on what we're going to do with this memory. And let's see, it's called, yes, madvise is a system call. So we can advise the kernel that we are not going to use it. So, and we're actually referring to both of these. We're saying we're not going to use the ping file anymore in any mapping to it. And in that case, the kernel will throw away our private memory because we're not going to use it anytime soon. And then it will point us back to the real map, or to the mapping that actually can get written back into disk if it's changed. And the issue is that in the implementation of copy on write, there's a race condition that basically means that if these operations happen, the copy on write and the discarding and moving the pointer back for the virtual memory, if those happen at around like at the same time and at their time correctly, then you can have a situation where, because copy on write is happening, it will move the pointers back of the virtual memory back to this part of RAM, but it won't complete the copy on write because it was as if the copy on write had already been completed, and that will cause that write to actually happen in the memory that will then get written back to disk. So then you actually changed the ping command on disk, which is a problem. So if we look at the code for that, I have this file here. It's based off of Caldonibans, if I'm pronouncing that correctly, exploit. If you just look up GitHub Caldonibin dirty cow exploit, it's the first thing that will come up. I just removed a lot of stuff to try and clean it up and make it faster and easier for me to explain. So anyway, what we have here is we have our map, which is a pointer into to our virtual memory of the mapping of the file. So the pointer will be the same, but where it points to on actual RAM will be constantly switching between the mapping that translates, that can get written back to the file, and our own private mapping. We have stat, which we need to get the file size, and that works basically the same way as the stat command. So like we can get the size here. Name is the file we're going to change, and contents is what we're going to write to it. So we start up these two threads down here. And these threads are going to run two system calls for the most part that cause that race condition that I showed, where we're constantly throwing away the memory and doing the copy on write. So after we open our file, map it into memory, This is private, so that that allows it to be discarded and point us back to the other mapping. We'll start up these threads in this madvise thread. As you can see, all it does is constantly runs this madvise saying we don't need the memory anymore. Go ahead and throw it away. And our other thread gets a file descriptor into our memory, and then gets that file descriptor to point to where our memory mapping is and writes to it. And that also happens 100,000 times, hopefully at the same time that the madvise is happening. So we can compile this. Nice error sign. Need the -o, of course. We can compile this, and let's just check again. If we stat admin lists, we are not allowed to write to it. If we cat it, it says user 01, and then if we run our exploit, and let's say we want hacker to be our new admin, we can now cat it again, and we see that hacker has now been used to overwrite the original contents, which was user 01. And that's been used in the wild to get privilege escalation. Again, you can do that on programs like Ping, so you don't need to contrive an example. And yeah, now you know, we got our millions, and we're living in a country that doesn't have an export treaty with the U.S. And yeah, so I'm gonna make a CTF based on this. I'll try to come up with good hints that don't just tell you exactly what to do. Like, I don't know quite yet how I'm gonna do that, but yeah, I'll do that. And if you're interested in knowing exactly what is the cause of the race condition, you can find, this is patched by Linus Torvalds. I think actually, never mind. Signed off by Linus. You can find the commit. It's on GitHub. That patches this. It adds a flag to this file, and then that flag is used as a check that can end this process early. If you're, yeah, so if you're interested in knowing how that works, you can totally free to read the entire Linux kernel source code. But yeah, thanks for watching. See you next time.